We're going to begin working some sample problems on colligative properties. Colligative properties are those properties, physical properties, that change the condition of a solution. Just by adding salt to water, we change the behavior of that solution in terms of things like osmotic pressure, boiling points, freezing points, and vapor pressure. Colligative properties do not depend on what the solute is, just how much of the solute you have. In our first sample problem, under our Objective 3, Colligative Properties, we're being asked to calculate what is the osmotic pressure. So we're looking for pressure, osmotic pressure, of a solution formed by dissolving 44.2 milligrams of aspirin C9H8O4. We're going to dissolve that into 0.358 liters, and we'll have the temperature recorded as 25 degrees Celsius. Osmotic pressure, that flow of water across a semi-permeable membrane. By adding aspirin, a solute, into water, we create a solution and therefore set up a pressure gradient in which water will be pushed or forced across that semi-permeable membrane. Now there is a formula for calculating osmotic pressure, which is capital Pi for pressure, just a little bit different than P for the gas laws. And that's equal to molarity times the gas constant R times the Kelvin temperature T. Pi equal mert, where M stands for molarity. However, since we really don't need to memorize so many equations, we can think of osmotic pressure really falling under a Pov-Nert equation. Now the reason that that is technically a different type of pressure is that this is for ideal gases. And of course we are not working with gases in this problem, it's working with solutions, but nonetheless the formula will still work for us. Osmotic pressure, P, times V, the volume, equal nRT. And I understand that moles, N is standing for moles. Keep in mind that molarity is defined as moles per liter. Big M is moles per liter. So it really is just a rearrangement of the Pov-Nert equation. So since that's the one we're most familiar with, no sense memorizing a second pi equal mert, but we can just memorize Pov equal Nert and know that it not only applies to ideal gases, but it also applies to solution chemistry as well. We are looking for pressure, our P variable. The volume is given to us, and it must always be in a liter, and in this example it is 0.358 liters. N stands for the number of moles. That looks like a mole map problem, doesn't it, where we're given a mass. So let's just do a little side margin here. Converting my grams to moles, so 0.442 grams of C9H8O4. Converting that to a mole says we are going to require a molar mass. Let me add that up for you. Do it with me on your calculator, just to be a calculator buddy. We have 9 carbons at 12 apiece, so 12 times 9, plus 8 contributing from the hydrogen, and then 16 times 4. I get a total molar mass of 180 grams. Let me get that written here. So doing my mole map work, looks like I have 0.0442 divided by 180, and I get a small number, as it makes sense. We had a milligram there. I'll write that in scientific notation. 2.45 times 10 to the negative 4th moles. There's my N value, the number of moles of aspirin in that solution. 2.45 times 10 to the negative 4th moles. Now, R is a gas constant, 0.0821. That will tell us that our pressure unit will come out in an atmosphere, which osmotic pressure typically is recorded in atmospheres of pressure. And then our temperature of 25 Celsius, add 273 and we come up with 298 Kelvin units. So recall how we add 273 to turn Celsius into Kelvin. So let's hit our number of moles, 2.45 E negative 4 times the gas constant, 0.0821, times the temperature of 298. And now we'll divide that by the volume, 0.358. So N times R times T divided by V, and pressure comes out to be 0.0167, so 016, I'll round, 0.0168 moles, atmospheres for pressure. Let me get that neater. Alrighty. So here's an example where we took pressure, osmotic pressure, equal molarity times R times T, and just rearranged it to a more familiar equation, PUV equals NERT, plug and chug in, and we arrived at our answer, 0.0168 atmospheres. We'll continue reading. Our second example problem. This deals with boiling points. It says the normal boiling point of carbon tetrachloride, CCl4, has a boiling point of 76.8 degrees Celsius. Its boiling point constant, Kb, is recorded as 5.02 Celsius degrees per molal unit. These are two things that we would need to know, either even from a chart or provided for us in the story problem, to solve a colligative type property equation. We're asked to calculate the new boiling point. What is the new boiling point? If I turn my solvent into a solution by dissolving 15 grams of decane, C10H22, and I'm going to place that into 49.5, and that's grams of carbon tetrachloride. So these two values here are recorded as knowns, and so that provided information there is what we would need to start solving the problem, ultimately being asked to know the new boiling point. The new boiling point can be found by calculating how much it changes by, and we know that boiling points elevate, they raise. Boiling points increase just by sprinkling something and creating a solution. That's found by knowing the molality, the K constant, and something called the Van Hoff factor, which deals with electrolytes. Now, if I look back at our solute, C10H22, it's called decane. Decane is a molecular compound, all made of nonmetals. We know it to be what's called a non-electrolyte. It does not break apart or dissociate and form ions in solution. So the Van Hoff factor here is simply a 1. It does not break apart. Now, M stands for molality, and we've got a little work to do here to find molality. Molality we know to be moles of solute per kilogram of solvent. So we have a little bit of mole map work to do. We are given 15 grams of C10H22, and to convert that into a mole unit will require its molar mass. So 12 times 10 coming from the carbon, add on 22 from the hydrogens, and the molar mass is 142 grams. 15 grams divided by the molar mass of 142, and I get 0.1056, shall we say 0.106 moles, that's a mole conversion, of our C10H22 called decane. So 0.106 moles per kilogram of solvent. We come back up here, and 49.5 grams of carbon tetrachloride converted to a kilogram is 0.495 kilograms of solvent. So that mole number, well, it's still on my calculator, divide by 0.495, and the molality is 2.13. Alrighty. So back up here, we now know the molality to be 2.13 molal units. The K constant was given to us in the reading. It was 5.02 in Celsius degree per molal is that unit for K constant. What that means is that for every 1 molal solution, that boiling point is going to elevate 5.02 degrees. And we said the Van Hoff for any molecular compound, any non-electrolyte, remains as 1. Let's calculate for our change in the boiling point. 2.13 times 5.02, and I get 10.71, we'll say. Now, the normal boiling point was recorded as 76.8. Boiling points elevate, so we have to add 10.71 to find the new boiling point, plus 76.8, and that gives us a new recorded value of 87.51 degrees Celsius, the new boiling point of our solution. Pure carbon tetrachloride boils at 76.8 degrees. By dissolving a solute and creating a solution, it now boils at a much higher temperature, about 87.5 degrees. Let's continue reading a third example problem. This third example problem has a freezing point involved. Let me add a slide so we have some fresh space to work. So here is number 3. It reads, calculate the new freezing point of a solution made by dissolving 13 grams of potassium sulfide, that's K2S. We're going to dissolve that into 150 grams of water. And the K constant for the freezing point of water is given as 1.86 degrees Celsius per mol solution. It's also assumed that we know that the normal freezing point of water is 0 degrees Celsius. Now, water in any solvent is going to lower its freezing point by creating a solution. So boiling points elevate, freezing points depress. They decrease. The change in the freezing point is found by knowing the molality times the K constant times the Van't Hoff factor. The Van't Hoff factor really is just taking into consideration excuse me, those compounds that are electrolytes and dissociate. When K2S, potassium sulfide, dissociates, and what that means is if we take this solid, place it into a water to create a solution, we're going to get 2 aqueous ions of potassium and 1 aqueous ion of sulfide. The Van't Hoff factor here is a total of 3 particles, 2 Ks and 1 S. So the Van't Hoff factor for this electrolyte, K2S is indeed an electrolyte. We commonly call that a salt, if you will, a soluble salt, is going to be 3. We also need to do a little molality work. Molality, we know, is moles of solute per kilogram of solvent. So we need to do a little mole map work. 13 grams of K2S. Using its molar mass to convert that, let me add that 39 times 2 from potassium, a 32 from the sulfur. Molar mass here is 110 grams. 13 divided by 110. Hang on, hit the wrong key. 13 divided by 110 grams gives me a mole value of 0.118 moles K2S. So the change in the freezing point is now, oops, I have to do that molality. I have moles, 0.118, I got ahead of myself, 0.118 moles of solute per kilogram of water, 0.15 kilograms. So I divide that by 0.15 and I get 0.787, should we just say 0.79 molal units. There's my molality. I was getting ahead of myself there. 0.79 molal units. Freezing point constant of water, 1.86 Celsius degree per molal, and as discussed, the Van't Hoff factor of 3 particles. So molality times the K constant of 1.86 times the number of particles being 3, and the change in the freezing point, 4.396, we'll say 4.40 Celsius degrees. If the normal freezing point of water is 0 degrees Celsius and freezing points decrease, they depress, we're going to need to subtract 4.40 degrees to find the new freezing point, And again, just kind of tabulating normal freezing point minus how much it changed by is going to be at a negative 4.4 degrees Celsius. Let me read through a next example problem. And this will do with finding molar mass. Okay, we've done a lab like this. So let me take a quick look here. Lauryl alcohol is obtained from coconut oil and is used to make detergents. When 5 grams of lauryl alcohol is put into 0.1 kilogram of benzene, it freezes at 4.1 degrees. What is the approximate molar mass of the lauryl alcohol? We'll need to know benzene's normal freezing point, and that is given as 5.5 degrees Celsius. And we'll need to know its freezing point constant. Freezing point constant K is 5.12 degrees Celsius per molal unit. Okay, so in this problem, we've got quite a few steps to get back to ultimately finding the molar mass of the lauryl alcohol. Again, notice that it did not give us the formula for lauryl alcohol. We could just go to the chart and add up the weight. So a little bit more involved. We know that the change in boiling point is molality times K times the Van Hoff factor. You can look at this lauryl alcohol and know that it's a molecular compound. It's an organic molecule. And know then that the Van Hoff factor will be a 1. Since it is a non-electrolyte, as all organic compounds tend to be, non-electrolyte, the Van Hoff factor comes out to a 1. If we know that the normal freezing point is 5.5 degrees, and it froze now at much lower temperature of 4.1 degrees, how much should it change by? Well, a little subtraction here, in the change in the freezing point, I don't know why I wrote B here. The change in the freezing point is 1.4 degrees. So if it normally freezes at 5.5 and now it's freezing at 4.1, let's solve for that change in freezing point as 1.4 degrees Celsius. We don't know molality. We do know the freezing point constant of 5.12. And we know that the Van Hoff factor is 1. Let's use that information to pull out the molality of our solution. So 1.4, the change in the freezing point, divided by the K constant of 5.12, tells us the concentration of that solution is 0.273 molal units. All right, so step 1, solve for molality. Now that we know molality, keep in mind that we can also use its relationship as moles of solute per kilogram of solvent. And hidden in this variable here, ultimately, we'll be able to pull out the molar mass of our solute. So let's plug and chug this out. We have 0.273 molal units solved from our first step. We'd like to know the number of moles, so that's going to be my target variable. And we put that into 0.1 kilograms of benzene. See this in the sample problem, 0.1 kilograms. So let's just cross multiply and solve for the number of moles. Cross multiplying will give us 0.0273, however many decimals you'd like, moles of solute, the lauryl alcohol. Well, we're almost there. We know that moles has a relationship of grams over molar mass, and so ultimately this is our target. Rearranging there, molar mass can be solved by knowing grams over moles. That's typically the unit provided for molar mass, gram per mole. Well, how many grams of lauryl alcohol did we use? Looks like 5 was provided in the story problem. So we have 5 grams of lauryl alcohol. We calculated the mole, 0.02734. Gram divided by mole, 182.857, so let's write that as 182.86 grams per mole, the approximate molar mass of lauryl alcohol. Step 1, use the change in freezing point to target the molality unit. Step 2, now that we know molality, cross-multiply that with a kilogram of solvent and pull out mole. Step 3, use our relationship of grams per mole to solve for molar mass. We have one more in our story problems for this particular objective. Let's do a read through here. Lysozyme is an enzyme that breaks bacterial cell walls. A solution containing 0.150 grams of this enzyme is in 210 milliliters of solution. And it has an osmotic pressure, so I'm going to record that as capital Pi, osmotic pressure of 0.953 torr. And that's another name for millimeter mercury, which, by the way, matching R constant is 62.4. Alrighty, so if pressure is in an atmosphere, the R constant is 0.821. If pressure is in a torr, the gas constant that matches 62.4. And the third unit there is a kilopascal, and that's 8.31. So those are the matching R constants depending on what unit of pressure they give us. So here's the value of R depending upon the pressure unit. In this example, they gave us torr, millimeter mercury, so 62.4 ends up to be the R constant. And then the last little piece of information, it says we're going to do this at 25 degrees Celsius. Let's find the molar mass. The molar mass of this enzyme, lysozyme, and don't be surprised, enzymes are huge molecules. I would anticipate this being quite a large number, and sometimes that scares students when they see a large molar mass. But here's what we know. I know that pi equal mert. Osmotic pressure is molarity times the R constant times the temperature in a Kelvin unit. But why memorize a new equation when we know one from the gas laws, PV equals nert, and that works just as well. Knowing typically that is just a little bit different because this is solution chemistry and this is gas law chemistry, but this equation is familiar to us. So we'll go ahead and use it. The pressure is given to us as 0.953 torr. The volume is 210 mils, but remember 0.21 liters. It has to be in a liter unit. Pulling out N, the number of moles, because knowing N, moles, that's where hidden molar mass is. R, and matching R constant, 62.4, and 25 Celsius in a Kelvin unit is 298 Kelvin. Let's pull out N, the number of moles. So 0.953 pressure times 0.21 volume divided by 62.4, the R constant, divided by 298, the Kelvin temperature. And N here comes out to be 1.076 times 10 to the negative fifth mole units. Recall that moles is calculated by grams over molar mass. So to rearrange that, we know molar mass can be found by taking grams over moles. Well, how many grams did it give us there? I have to back up. 0.150 grams. The mole we just calculated of 1.076 times 10 to the negative fifth. And we'll have our molar mass. Hitting with me, it's a very large number as anticipated. 13,937.34 gram per mole units. We've worked two types of problems finding molar mass, one with a change in temperature and one with an osmotic pressure. And ultimately, we're just pulling out moles, n variable. And once we know moles, we take the mass divided by mole and pull out the formula weight.